When you think about paleontology, you might picture these quiet academics just dusting off old bones. But sometimes it is absolutely a spectator sport, filled with these intense, decades-long rivalry.
Oh, it's so true. The history of the field is just littered with them. I mean,
Yeah.
you think about the bone wars between Cope and March back in the late 1800s.
Right.
They basically spent their entire fortunes trying to one-up each other, discovering new species. It left them both penniless, but it also completely blew open our understanding of dinosaurs.
And today we are diving into a scientific debate that has echoes of that same kind of rivalry. And it's all focused on one terrifying question. Could Quetzalcoatlus, the biggest winged giant in the history of our planet, actually fly?
And what's so fascinating here is that this isn't just a simple question of, how big the bones were. It's a direct confrontation with the laws of physics. We're
Really?
talking about the absolute limit for powered flight, and it opened up this massive paleontological can of worms that took nearly 50 years to sort out.
And that is our mission for you in this deep dive. We're going to unpack that original discovery, explore the really intense challenges from skeptics who said flight was just impossible, and then look at how the modern consensus finally confirmed it. It's a perfect story of how just a few fossil fragments can lead to these huge, huge battles of interpretation. So let's go back. Let's start in the mid-1970s, where this whole thing kicked off. The first discovery was made by Douglas A. Lawson.
Yeah, and he was just a kid at the time, really. Only a 22-year-old grad student at the University of Texas.
And the confidence he showed, right from the get-go, it's kind of amazing. He published his first paper in 1975, and the title just left no room for doubt.
None at all. It was called pterosaur, the latest Cretaceous of West Texas.
Yeah.
Discovery of the largest flying creature. He was making a definitive statement. This thing flew.
He named it Quetzalcoatlus, after the Aztec feathered serpent god Quetzalcoatl, which makes sense for the location. And eventually, we ended up with two species. The really big one, Q northropi, and a smaller one, Q lawsoni, which was named after him.
And we should probably mention, the term pterosaur is just an older word for what we now call pterosaurs. The flying reptiles that lived alongside the dinosaurs.
The location of the find is so important, too. Big Bend National Park in West Texas.
It's a paleontological jewel box. And the timing is everything. Those fossils were found just 1.5 meters below the KPG boundary.
And that's the layer that marks the asteroid impact, 66 million years ago. So this creature, Q northropi, was living right up until the very, very end, one of the last and certainly the largest animal to ever soar in our skies.
Which brings us to the scale, the very root of this whole conflict. Because what Lawson pieced together suggested a creature with a wingspan of over 10 meters.
It's hard to get your head around that. 10 meters, that's wider than a school bus.
And remember, they didn't have a complete skeleton, not even close. They had bits and pieces from a few individuals, wing bones, some neck vertebrae, a jaw. So they had to use smaller, more complete relatives to kind of scale it up.
Which is exactly why the estimates were all over the place for years, right? I've seen everything from 5 meters up to 20.
Exactly. But even at that conservative 10-meter estimate, when this animal was on the ground, it would have stood as tall as a modern giraffe.
Okay, so that leads us to the weight paradox, the thing that caused all the trouble. Because, like birds, it had hollow bones. So for its size, it was actually incredibly light.
Right. The estimates put it somewhere between 100 and 200 kilograms. So about the same as a full-grown male lion.
And if you compare that, the heaviest flying bird alive today is the Cory bustard. It weighs maybe 20 kilograms.
And it struggles. If you watch one take off, it's this frantic, running, flapping thing. It looks like a huge effort. So the question becomes, how could a creature 10 times heavier possibly get off the ground?
It's a huge scientific problem. And just to be clear for everyone, pterosaurs were the very first vertebrates to evolve powered flight. They weren't just gliders.
And crucially, they are not the ancestors of birds. This is a classic case of what we call convergent evolution.
So two totally separate family trees, one leading to birds, one for these flying reptiles, both solving the problem of flight, but in completely different ways.
Precisely. The engineering looks similar, but the machinery underneath is totally unique.
Okay, so let's dig into that weight paradox. You have Lawson saying it absolutely flew, and then physics saying, no, it didn't. The skepticism wasn't just casual, it became a really systematic attack on the idea.
The first major shot across the bow came almost immediately from an engineer named Crawford Greenwald. He basically launched a direct assault on the whole idea using modern birds as his model. He looked at the ratio of the upper arm bone, the humerus, to the total wing size.
And his conclusion was pretty damning.
It was. He basically said, look, there are no modern animals that even come close to these proportions. A 200-kilogram flyer. The whole idea, he said, was far-fetched. He kind of set the barrier that the paleontologists now had to overcome.
And then it just snowballed from there.
It really did. 2 other papers came out that just added fuel to the fire. The first one created a model for the absolute physical limits of flight.
And that model said the limit was about 40 kilograms with a 5-meter wingspan.
Right. Quetzalcoatlus was 5 times heavier and twice as wide. So this wasn't just an opinion. It was a model based on aerodynamics that basically said this creature couldn't exist as a flyer.
And the second paper just went for the jugular. It attacked the weight estimate itself.
Yeah, they argued that 100 or 200 kilos was way too low. Their estimate was over 500 kilograms. I mean, at that weight, it's game over. There's no way it's getting airborne.
Which led to this idea, this convenient explanation called the ancestry hypothesis. The idea that, well, maybe smaller ancestors could fly, but by the time it got this big, it was grounded.
Kind of like an ostrich. You know, its ancestors could fly, but the modern ostrich can't. It seemed like a logical way out of the problem. You get to keep the giant wings, but you don't have to explain how it flew.
But that's not where the story ends.
No, not at all. This is where it gets really, really interesting. Because the scientific community had more or less written it off as flightless. And the question became, how do you fight back against physics?
Enter the paleontologists Mark Witten and Michael Habib. They basically decided to take the fight right back to the fossils. Their rebuttal was this big paper with a very pointed title.
With a bit of a mouthful, yeah. On the size and flight diversity of giant pterosaurs.
Yeah.
But the key part was their central argument. Using modern birds to model a pterosaur is just, well, they called it silly.
It's a fundamentally flawed comparison.
It is. They argued that pterosaurs weren't birds. Their entire anatomy, their biomechanics, evolved on a completely separate path for millions of years.
Yeah.
You can't just swap the numbers from a pigeon and expect them to work.
And they backed this up with a huge discovery from re-examining the actual bones. The very bones Greenwald had used to say flight was impossible, the upper arm bones.
This was the real kicker. Witten and Habib looked at the bone's internal structure and density and realized something incredible. The humerus of Quetzalcoatlus was, in key places, twice as strong as anyone had assumed.
Twice as strong. So the engine powering the wings was double the capacity everyone thought?
Exactly. It completely undermines Greenwald's original argument. If the arms are that much more powerful, then the entire equation for takeoff and flight changes.
And that strength is what led to the big breakthrough, right? The takeoff solution.
The quadrupedal launch.
Yeah.
Yeah. This was the game changer. Instead of running and flapping like a bird, they realized Quetzalcoatlus probably launched from all fours.
So it would crouch down and then use those incredibly powerful arms to just vault itself into the air, like a massive 4-limbed push-up.
A colossal jump, basically. It would generate enough power and lift in that one explosive movement to get airborne, and then it would transition to flapping and gliding. It completely bypasses the need for a long runway, which is one of the big problems the skeptics pointed out.
Wow. And around the same time, the weight estimates started to come back down, too. The 500-kilogram idea was shown to be pretty unlikely.
That's right. The models got better,
Yeah.
and the consensus settled back into that 100 to 150-kilogram range for a large adult. Still huge, but suddenly, with this powerful launch mechanism, it was back in the realm of possibility.
And they even rethought the wings themselves. They weren't just simple skin membranes.
No, they were more like reinforced sails. They had these stiffening fibers running through them, which would have made them incredibly strong and stable, perfect for catching thermal updrafts and just soaring for hours like a giant sailplane.
So when you put it all together, the consensus just completely shifted.
It did. The debate is no longer if it could fly. We know it could. The debate now is all about the incredible logistics of how a creature that big managed such an amazing feat.
But, and this is always the case with paleontology, solving one big mystery doesn't mean the story is over. That scarce fossil record means a lot of questions are still on the table.
Oh, absolutely. I mean, answering one question just opens up 5 more. We solved the big one. It flew. But the details are still fueling a ton of research. For instance, why the long legs? They were longer than a lot of dinosaurs that lived at the time, which is a very strange, heavy feature for an animal built for the air.
And what about the different sizes? You have the smaller Q. lawsoni. Is it possible the young ones were agile flyers, but as they grew into these massive Q. northrop adults, maybe they became more reliant on gliding?
That's a great question. Did they lose that sustained, powered flapping ability as they got bigger? And then there's the habitat. It lived inland in West Texas. Gliding on that scale usually requires strong, predictable air currents like you'd find over the ocean. How did that work so far from the coast?
And the diet. What did it eat? They found fossils near big sauropods, so maybe it was a scavenger like a giant stork using its long neck to get into carcasses.
Or was it an active hunter? And if so, how does something that big and, potentially awkward actually catch prey?
And the most practical question of all, how in the world did it land? Landing a school bus-sized glider safely seems like a bit of an engineering nightmare.
It really does. But this whole story, from Lawson's confidence to the intense pushback and then the final vindication by Witten and Habib, it's just a perfect showcase of how science works. It's about that rigorous debate and being willing to throw out your old assumptions when new evidence comes to light.
It's just amazing to think about the sheer scale of this animal. Pterosaurs were at the absolute peak of their evolution, producing these true giants of the sky, right when their time was just abruptly cut short, 66 million years ago.
Which leaves a pretty interesting thought for you to explore. Given the incredible size, the sheer power of the largest creature to ever fly, what kind of engineering challenges or even societal changes would we be facing if these silent, 10-meter-wide giants were still soaring over our modern cities today?